Can hear me clearly? Kindly show me raise your hand quickly. Sakina, Muntaha, Romasa. Can you hear me, Sakina? जबकि आवाज नहीं आई मुझे. Yeah. Okay, fine. Let's get started. Let's put that up on button. Continue from where we left in our previous lecture. Please lower your hands, guys. We were doing periodicity and we had to do the trends. And the trend that we were currently doing was the trend of ionization energy down the group and across a period, right? So let's get started with this. So what happens to the ionization energy as we go down the group? Any guesses? First, to understand the trends of ionization energy, you need to know all the factors which affect ionization energy. So what are the factors that affect ionization energy?
Nuclear charge.
That's one. Okay, fine. Nuclear charge.
Shielding effect. Size of the atom.
Shielding effect. Yeah, what else?
Size of the atom.
So atomic radius. Fourth one is the charge density. Charge density is a concept which relates the two atomic radius with the nuclear charge. Okay. Charge density by definition is the charge per unit volume. Okay. So volume represents radius and charge represents nuclear charge. Now, if I increase the nuclear charge, it's going to increase the ionization energy. Increasing the shielding effect is going to decrease the ionization energy. So negative impact, increasing the atomic radius is also going to decrease the ionization energy. But increasing the charge density is going to increase the ionization energy. Okay. That's how they are related. Okay. So let's talk about the trend going down the group of ionization energy. So what happens to the atomic radius down the group?
Increases.
Because of that, the charge density also decreases, right? Charge density decreases. Shielding effect. How about that? Shielding effect depends on the number of shells, total number of shells. So as we go down, the shells increase. Oh, Sakina, can you not hear me clearly?
Sakina left, I think.
She does? She doesn't. Is the weather not good there? Is it raining?
No.
No? Okay. All right, so shielding effect increases as we go down the group because the number of shells are also increasing, and as a result of these factors going down the group, the ionization energy decreases. Okay. That's that, going down the group. Now, how about going across the period? Well, first of all, did you guys understand this trend? Going down the group, what happens to the ionization energy? This is the entire
Decreases.
trend. Okay, fine. So this is good, right? Okay, let's move on to explaining the trend across the period. So across the period, the nuclear charge is increasing. But since the period number remains constant, so therefore the number of shells are constant, right? All atoms are being added to the same shell. If you take an example of period 3 elements, all atoms have their electrons being added to the third shell, right? So the number of shells are staying constant, therefore the shielding effect, which depends on the number of shells, also remains constant. Okay, shielding effect is constant. Because the shielding effect is constant and the nuclear charge is constantly increasing, therefore the electron density will be pulled inside, okay, because nucleus is pulling it in, but the electrons are not increasing in strength, right? Electrons are staying constant. So because nuclear charge increases, but the shielding effect remains the same, therefore going across the period, the atomic radius is going to decrease, right? The nucleus is going to pull the electron density towards itself. So now the atomic radius decreases, nuclear charge increases, shielding effect remains constant. Hence, the charge density is going to decrease because charge density is inversely related. Charge density is going to increase because it's inversely related to the radius and directly related to the nuclear charge. So decrease in radius and increase in nuclear charge, both of them favor an increase in charge density. And hence, because charge density is increasing, this will result in an increase in ionization energy. So in general, the ionization energy increases as we go across the period. Okay? You understand this? This is the trend across a period from left to right, okay? All right. So we've studied across a period and down the group. Now we need to study, we are still studying across a period because there are some more pieces of information that you need to know across a period. Let's take an example of period 3 elements. Even though ionization energy constantly should increase across a period based on the general trend, there are a few exceptions to the general trend. Okay, so period 3 starts from sodium, right? After sodium comes magnesium, then aluminium, and silicon, phosphorus, sulfur, chlorine, and argon. Okay, can add the number of protons accordingly: 11, 12, 13, 14, 15, 16, 17, 18. Now, as you go across this period from left to right hand side, what happens? Going across the period, all of these factors apply, right? Nuclear charge increases, the shielding effect stays constant, atomic radius decreases, and charge density increases, due to which ionization energy increases going across the period. If you were to draw this out on the periodic table, these elements would look somewhat like this, right? If this is the periodic table, so we're talking about these elements, right, at the bottom. 1 second. We're talking about this line, right, the second line, because you also have hydrogen and helium over there. This is period number 1, this is period number 2, and this is period number 3, right? Now, if you look at the period number 3, in period number 3, element that is present right over here, this one, an element present right over here. Okay, These two elements that you have in the corners of the periodic table. Do you see these corners in between group 2 and group 3? 2A and 3A basically. These are the exceptions to the general trend. Meaning I'm talking about which two elements. Can you guys identify them over here in this period? Which of these are the exception?
Beryllium.
I'm talking about period 3. This is period 3 given over here. Beryllium is in period 2.
Magnesium and aluminum.
Aluminum.
Yes. Sakina, you're in class? Sakina, class no?
No, sir, she's not here.
Is this Naila?
Ji, sir.
Okay. Now, this is from magnesium to aluminum. Okay, yes, correct. Good job, Naila. So this is group 2A, group 3A. So you can remember it this way, okay? These two are the exceptions to the rule, meaning in general, ionization energy should increase in general, but from magnesium to aluminum, it decreases. Okay, it's an exception to the rule. And the second exception lies to the right-hand side. You guys remember nitrogen, oxygen, fluorine, the elements beneath it. So basically it's phosphorus and sulfur. Because you also have the nitrogen, oxygen, fluorine, nitrogen, oxygen. On top of them. Sorry, are you saying something? Anyways, nitrogen and oxygen and phosphorus and sulfur. Okay. So we are talking about period 3 right now. So as you go from phosphorus to sulfur, ionization energy also does not follow the trend, it decreases instead. These are the two exceptions to the rule. And now you've studied this, that elements which are, sorry about that, elements which are in the same group, they have similar chemical properties. So because these elements, magnesium and aluminum and phosphorus and sulfur, they show an exception to the trend. So elements which are in the same group but belong to period number 2 will also show an exception to the ionization energy trend. As someone of you mentioned this, from as you go from beryllium to boron, yes, that's also an exception. And then as you go from nitrogen to oxygen, and period number 2, that's also an exception because instead of increasing, it decreases instead. Okay. Now we're going to draw the graph and we're going to study the exceptions and why exactly do these exceptions exist. Okay. Give me 1 second. Okay guys, so ये trends जरा देख लेते हैं अब हम कि why are there exceptions to the rule as we go from magnesium to aluminum and phosphorus to sulfur. Okay. Let's draw the graph of ionization energy against atomic number or proton number. Sodium, magnesium, it's going to go up, but after magnesium, it's going to come down. Aluminum. Then silicon goes up, phosphorus goes up, but then sulfur again falls. Then chlorine goes up and argon also goes up. This is a sort of graph we expect to have when we are looking at ionization energy. Okay, so if you guys can see, can easily identify the magnesium, aluminum, then silicon, then phosphorus, sulfur, chlorine, and argon. Now, over here in this particular graph, the exception is present right over here as we go from magnesium to aluminum, right? Because as you look at the overall graph, the overall trend is an increasing graph. But there are these two exceptions, right? These two drops in the graph level. So the first drop is as you go from magnesium to aluminum. And the second drop is as you go from phosphorus to sulfur. So now let's study why exactly do these exceptions occur. Does anyone know why are there these two exceptions? Does anyone know the reasoning of magnesium to aluminum and the reasoning of phosphorus to sulfur?
Because of the shielding effect.
Which one is because of shielding effect? First one or the second one?
Magnesium and aluminum.
No, it's not actually the shielding effect. Shielding effect for both of them is the same. Okay, let's study this in detail now. If I were to ask you to draw the electronic or to write down the electronic configuration of magnesium and then followed by aluminium, you'll be able to answer this question then. Okay, so magnesium and aluminium, let's write down the electronic configuration. Magnesium is going to be, help me out guys, 1s2, 2s2, 2p6, and 3s2, right? Aluminium is going to be 1s2, 2s2, 2p6, 3s2, 3p1. Okay, yeah, shielding effect. Someone said shielding effect, right? Yes, your answer is correct. I actually didn't notice that. Yes, shielding effect does play a role over here. Now, can you explain how does the shielding effect play a role over here? Which one should have
Because
more?
like all of the electrons are here, and like the last valence electron that's free. So the nuclear charge on it, it's like not as much.
Nuclear attraction, yeah. Okay, great, fantastic. Yep. The outer shell electron of aluminium is in the 3p orbital, whereas the outer shell electron of magnesium is in the 3s orbital. So because all of these electrons are providing the shielding effect, compared to only these electrons in magnesium, therefore this outer shell electron of aluminum is better shielded, and because it is better shielded, lesser energy would be needed to remove it. So hence the ionization energy decreases. Okay, yes. And exactly the same reason applies as you go from beryllium to boron. Okay, beryllium and boron. Boron elements, electrons are also better shielded compared to beryllium. Right, let's look at the second exception to the rule. Second exception to the rule are going from phosphorus to sulfur. So does anyone know why? Is there any exception to go from phosphorus to sulfur? Both of them are the same, have the same shielding effect as well. This is phosphorus. Sulfur. So which one has better shielding? Oh, sorry. Why does phosphorus have a lower ionization energy compared to phosphorus? Yeah. Why does sulfur have a lower ionization energy compared to phosphorus? Any guesses? They have the same shielding effect, right? Both of them have shielding effect being provided by these electrons. The outer shell electron is in the 3p orbital. So now which one? Why does sulfur have lower ionization energy compared to phosphorus?
Because of the number of electrons present in outer shell.
Come again.
Is it because of the number of electrons present in outer shell?
What does that have to do with the ionization energy? Can you elaborate a bit?
The lesser the number of electrons, so more the shielding effect.
Well, actually, it's not the outer shell electrons that provide the shielding effect. It's the inner shell electrons, right? So both of them, these are the inner electrons. All of these from the 1s to the 3s. The same is the case here from 1s to 3s. So both of them have the same shielding effect.
Less ionization energy would be required, right? Like pull them away.
But both of them have the same shielding effect, right?
Yes.
Then why less ionization energy is required? That's the question. Well, this is because of a new phenomenon. Let's study it. If you look at the 3p orbital only, 3p subshell, the p subshell has three orbitals, right? Px, Py, and Pz. Same is the case here, Px, Py, Pz. Now, if you draw the electrons out, you have to fill them out using Hund's rule, right? Electrons will be half filled first. And over here, they'll be half filled first and then they'll be paired. Now, this pair of electrons that you guys can see, it's a pair of like charges, right? And these like charges are not gonna like each other, they're gonna repel each other. We call this repulsion, electron pair repulsion. It's because of this repulsion, lesser energy is needed to knock out this electron, okay? Because electron pair repulsion is present in paired orbitals, and there are no paired orbitals over here. In fact, if the orbitals are half filled, they're highly stable. And stable electrons are very difficult to remove. A lot of energy is required to remove them. So it's because of this pair of electrons and the electron pair repulsion occurs, and hence as a result of that, ionization energy decreases. Right. So the two reasons, the first one, for the first two elements from group 2 to group 3, that is from magnesium to aluminum, the reason was due to shielding effect, okay, better shielding in aluminum. And the reason for phosphorus to sulfur was due to electron pair repulsion. Okay. And same is the reason from nitrogen to oxygen. Okay, if you draw out the electronic configurations from nitrogen to oxygen, oxygen also has a pair of electrons due to which it experiences electron pair repulsion. And because it experiences electron pair repulsion, lesser energy is needed to remove that electron. Okay. With this, we've completed the variation across, down the group and across a pair of ionization energy. Next, we need to study about the electron affinity. I'm pretty sure you guys might have an idea of what electron affinity is. What is electron affinity? Opposite of ionization energy. How would you frame the definition of electron affinity? Electron affinity is going to be the enthalpy change when 1 mole of gaseous atoms accept 1 mole of electrons to form 1 mole of negatively charged ions. That's our electron affinity. So if we write it down mathematically, it's going to be like this. This is a gaseous atom, accepts an electron, 1 mole, and it forms a negatively charged ions gases. Energy change that took place over here would be your electron affinity. And more specifically, it's going to be called the first electron affinity. Okay. Now, if I add another electron to the A negative, I'll get another ion with A2 negative. And this enthalpy change will be called the second electron affinity. You can have the third electron affinity, and fourth and fifth and sixth and so on. Now, the second electron affinity is always going to be endothermic. First electron affinity can be endo, can be exo. It doesn't really matter. The first can be both. The second one is always going to be endothermic. Okay. Second one should always be endothermic. Now, can someone tell me why? Why is this always endothermic? Because A negative is already negatively charged and an electron is also negatively charged. So when like charges, they come close to one another, they will definitely repel each other, right? So we need high amount of energy in order to overcome that repulsion and make this reaction possible. So therefore, the energy that we provide, the activation energy is very high. Hence this reaction is endothermic. And it's always going to be endothermic from here onwards. Okay, meaning the third electron affinity is also going to be endothermic. The fourth will also be endothermic and so on. The affinity is exactly the same as ionization energy, but the good thing over here about electron affinity is that we don't have any exceptions. So you just need to know a simple trend. And that simple trend is as you go up the group and as you go across the period, the electron affinity will always increase. Okay, that's it. That's the trend of electron affinity. Then metallic character, metallic and non-metallic character. So do you guys know what metallic character depends upon and what non-metallic character depends upon? Metallic metals are good donors of electrons, right? They're electron donors. So because they're good electron donors, the left-hand side of the periodic table, left-hand side majority, they have relatively large radius. Because they have large radius, they have low charge density, due to which they have low electronegativity as well. It's because of this low electronegativity, elements on the left-hand side tend to become metals. Okay, metals are good electron donors. Electronegativity is the ability to accept electrons. So due to their low charge density, they have low electronegativity. They have a metallic character. And vice versa is also true, meaning if you look at the right side, they have a high electronegativity, the small radius, high charge density, high electronegativity, due to which they can accept electrons very easily, and because they are electron acceptors, they're non-metals. Okay, that's a general trend. You also have metalloids in the middle, like silicon and germanium, have properties of both metals and non-metals. Group 4. To that, we can study about the melting and boiling point trend. The trend of melting and boiling point is very variable. Different reasons are there. Explain different elements. I think that's it for today. We can stop here. It's a lot of information to retain. A lot of conceptual information, I should say. Let's make sure to revise the lecture today. Thank you guys for joining in. Take care. Allah.